So in this video, we're going to look at the bisection method. The bisection method, and is basically a method for solving equations on single variables. So basically, what you're looking at is a situation where fx is equal to 0, and essentially our aim would be to try to solve this equation. Now, one thing important to keep in mind is this method is not about just polynomial equations. The method is not restricted to any particular form of the function f of x. The only thing is the function be continuous over a particular interval. For instance, along with this, we'd be saying that we want to find the root or the solution of this equation on the interval ab, such that the values of x are within AB and that they satisfy the equation. And satisfy, of course, is an important term you have to understand. Just to recall, the solution of an equation, or when x satisfies an equation, it's said to be its solution. And by satisfy, we mean that when you substitute the value of x into the equation, both sides of the equation are balanced and equal. Now, the other important thing to keep in mind is the bisection method actually mathematically is based on the intermediate value theorem. And the intermediate value theorem is something you would have studied in Calculus 1. Basically, quick revision of it is as follows. So you're talking about some function f of x here, for instance. So along the y-axis, we're measuring f of x and x over here. And here's some value a and there's some value b. Now, if we go across here, this would of course be f of a, and this value here, it was f of b. Now, in between f of a and f of b, one can choose any value. For instance, let's say we call this sum f of c. And obviously, because it's on this, if we go across there and go down here, this would in fact be c. Now, what the intermediate value theorem guarantees is that for any c belonging to this interval ab, which means it's between a and b, there will always be a c such that fc is also between fa and fb. So that's basically what the intermediate value theorem says. Now, one thing to keep in mind, the prerequisite necessary condition of the intermediate value theorem is that fx be a continuous function. Right. We will exploit this fact to in fact try to see how we can find the root of an equation. So now let's turn our attention again to the bisection method. Let's try to visualize what happens when we are looking for the root of an equation. When this happens, for instance, here's an example. Now this is some function f of x, and this value here, graphically, well, this is the x-axis and this is fx along this axis. Then this value, whatever value it might be, let's say r, is the root of an equation. And when x is equal to r, so when x is equal to r, f of r must be equal to 0, given the equation fx equal to 0 is what we're trying to solve. So x is equal to r is where clearly f of r is 0. We can see that. Those are the coordinates of that particular point as well. Now let's extend the idea to the point that, let's say this is the point A and this is some point B. And this is what as I said in the beginning, the bisection method, what we want to do essentially is solve the equation fx equal to 0. So fx equals 0 on some interval ab. So the idea is going to be that what is so interesting, what can we use, what idea is there that we notice where fx behaves, the values of fx behave a certain way when there is a root between a and b. Well, if you think about it, any values here on this side, so if we go between a and r, any value we choose will fall on the graph down here, which means they're going to be negative. And any values between r and b would be up here, which means they will be positive. So it seems to suggest that there is a change of sign. So negative on this side and positive on this side of the root. Now let's look at the other. There's only one other possibility, is this way. So in this case, what you see is here on this side, and if this is your A and this is B, for instance, we notice that if this is our R, then between A and R, we see the values are positive here, but they are negative on this side. So this indicates that there is a change of sign. And no matter what we do, what's interesting is if there is a root between A and B, we expect that there will be a change of sign for the values of F. In other words, F is positive here. As you can see, it's positive here, and over here, F is negative. So it means that to start with, if there is a root, if there is a root indeed on the interval AB, if there is a root of f of x, I should say, on the interval AB, then clearly f of A, all right, and f of B will have a different sign. Will have a different sign, and that's very important. That's the key idea we're going to use to develop this method. So let's go a little further now and elaborate on that a bit more. So what this means is that essentially what we're saying is that FA and FB multiplied together would be less than 0. Because if the sign of FA and FB is different, it'll be negative, because two negatives multiply to give a positive, two positives can multiply to give a positive. But a positive multiplies with the negative to give negative. So if FA product with FB is less than 0, this implies FA and FA this exactly, which is both FA and FB have a different sign. And if they have a different sign, then there is a root between A and B. Now here's what the bisection method says, or here's what one would logically do. Think of this as a search. So we're searching for the solution, searching for the root of the equation. So this means what we're saying is that, okay, this is our key argument. This is our key argument. Now, if I have the interval AB, one of the easiest things I can do is to split AB into two intervals. And what I can do is I can choose the midpoint of AB, which would be easy. Let's call it M. And M is A plus B over 2. So if M is A plus B over 2, then this means I can split the interval into two, AM and MB. Okay, that's of course, M will be somewhere between A and B, guaranteed, because it is a midpoint of A and B. Now, here's the interesting thing. So what you have is two intervals. Now, either what you'll do is you'll see FA and FM. And if the product of FA with FM, okay, is less than 0, that means the root is here. And the same way we can test if FM dot FB, this product, is less than 0, then the root is in the interval MB. Now, if the interval, whichever interval contains the root, we again go to that root, take the midpoint, again get two intervals, find the interval where there's a change of sign, and keep doing this till we actually end up being very close, either very close to the root, or f of the value, f of m, in fact, becomes 0. So this basically defines for us the bisection method.